Welcome back, friends. So, in this lecture, we shall study Maximum Power Transfer Theorem, presented by Hanamant S. Pidashetty, lecturer, Government Polytechnic, Mudol. So, Maximum Power Transfer Theorem states that the DC voltage will deliver maximum power to the load only when the source resistance and the load resistance becomes equal. If it is an AC circuit, the AC source will deliver maximum power to the load only when the source resistance is a complex conjugate of load resistance. So, where we can find the application of maximum power transfer theorem? So, normally, when you want to deliver power to load, some devices require certain amount of power, like say stereo amplifier, radio transmitters, communication equipments. So those require certain amount of power. So to provide a maximum power to these loads, we apply maximum power transfer theorem. Now, having said the maximum power transfer theorem, let us study proof of the maximum power transfer theorem. So, why is it the load resistance should be equal to the source resistance? Okay. So now here we make use of Thevenin's theorem. Now any network is replaced by a Thevenin network, Thevenin equivalent circuit, and then using this circuit we shall derive the maximum power conditions. Now, so here picturally the power delivered to the load is maximum when RL is equal to RTH. Now here the amount of power delivered to the load, that is PL, what I call PL is the amount of power delivered to the load, which is equal to I square into RL. So I square is the current that is flowing through that load resistance and RL is the load resistance. Now I said I will make use of Thevenin's theorem. So this network is replaced by Thevenin network. So in this, the load current IL is given by VTH divided by RTH plus RL. So I am making use of that formula in this equation. So now substitute I is equal to VTH divided by RTH plus RL. So this I will substitute in the above equation. So that is PL will now become PL is equal. So in place of I have to replace VTH divided by RTH plus RL. So VTH divided by RTH plus RL whole square into RL. That is PL is equals VTH square RL divided by RTH plus RL square. So I'll call this as equation number 1. Now, so condition for maximum power transfer. So in the statement itself we have told that to deliver maximum power, load resistance should be equal to the source resistance or circuit resistance. Now, how to check whether this will deliver the maximum power or not? So here we have learned that first derivative of a function will give you maximum or minimum. So I will calculate first derivative of that equation number 1 and I will equate it to 0 to get the condition for maximum power transfer theorem. So we have seen PL is equal to VTH square into RL divided by RTH plus RL square. Now if I derive this equation with respect to RL, what happens? dPL divided by dRL. So since RL is there in the numerator and denominator, so it is in the form U by V function. So which is V into derivative of U minus U into derivative of V divided by V square. So here VTH square is constant, I will take out, and first V, so that is denominator VTH plus VRL square, so that denominator I am keeping as it is, into derivative of numerator. Numerator I have RL, so derivative of RL with respect to RL is 1, minus numerator, that is RL, into derivative of denominator. Denominator I have RTH plus RL square. So the derivative of that is equal to 2 into RTH plus RL. Now divided by RTH plus RL raised to 4, because in the equation I had RTH plus RL square. So when you derive it in U by V, in the denominator we get V square. So that is V square is RTH plus RL raised to 4. So that is equal to 0 to deliver maximum power. Now, so when this equation become 0, when the numerator is equal to 0, so that is, so numerator I am making it is 0, that is RTH plus RL square minus 2RL RTH plus RL is equal to 0. I will just rearrange it, that is I'll take RTH plus RL common in this. So what is remained? So in the first, again RTH plus RL is remained, and in the second component just remained with the minus 2RL. So RL minus, so here equal to 0 is there. So in this condition, so in the second one it becomes RTH minus RL. So RTH plus RL cannot be 0, so hence RTH minus RL can be 0. So I will equate it with RTH minus RL is equal to 0. That gives me RTH is equals RL. So this is the condition for maximum power transfer. So to deliver maximum power, your Thevenin resistance, that is the circuit resistance. So we have replaced the circuit by a Thevenin circuit, so that Thevenin resistance should be equal to the load resistance R, and then only the maximum power can be delivered. Now, what is the value of this maximum power? So to calculate that, I'll again go back to the equation number 1, that is this equation. In this equation I will replace PL by PL max and RL by RTH. So since to deliver a maximum power, RL should be equal to RTH, so I will substitute those. So substitute RL equal to RTH and PL equal to P max in the equation 1. So that is PL max is equals VTH square into, instead of RL I have to put RTH now. RTH plus here one more RL was there. So I have replaced that with RL. So then whole square. Now here in the fraction part, there is numerators are so RTH, denominators there are 2RH, so 2RH square will become 4RTH square. So 1 RTH and a square will get cancelled, so just remain with 1 by 4 RTH. So that is PL max is equal to VTH square divided by 4 RTH. So since RL is equal to RTH, you can also calculate PL max is equal to VTH square divided by 4 RL. So that is the amount of maximum power transferred to the load. So here we got two things, that is, one is condition for maximum power transfer is RL is equal to RTH, and the maximum value of that power is equal to VTH square by 4 RL or 4 RTH. Now, steps to solve a network using maximum power transfer theorem. So, to calculate the maximum power transfer theorem, so we need to follow certain steps. Those are steps number 1, that is remove the load resistance from the circuit. So these steps are similar to the one which we have discussed in the Thevenin's theorem. That is remove the load resistance, find out Thevenin voltage, find out Thevenin resistance, and redraw the Thevenin's equivalent circuit. And so to deliver a maximum power, we have a condition, that is RL should be equal to RTH. Only then the maximum power is transferred. Hence you can find out the value of load resistance to which maximum power is delivered using this condition, and then you can also calculate what is the maximum power that is transferred, that is value of maximum power P max is equals V square TH divided by 4 RTH, that is VTH square, this is VTH square divided by 4 RTH. Now let us study one example here. So a circuit is shown here. Determine the value of load resistance that receives the maximum power from the supply source and value of the maximum power delivered to the load. So he is asking what is the value of load resistance should be connected so that it receives the maximum power. That is, he is asking what is the value of RL, and also he is asking to find out what is the value of maximum power delivered to the load. So what is Pmax? He is asking. So we should follow the steps and solve this network and find out what is RL and what is Pmax. Now, the first step says you have to remove the load resistance. So I have removed the load resistance and try to find out what is the voltage across these terminals A and B. So to find out voltage across A and B, so I need to find out what is voltage at point A and what is voltage at point B. So voltage at point A is nothing but voltage across R2, and voltage at point B is nothing but voltage across R4. To calculate those, so I can apply KVL to loops. So in the first loop, if I apply KVL, what it becomes? So VA is equals, or you can also go for voltage division rule also. Both are fine. So here voltage division rule, that is V into R2. So across R2 I want the voltage drop. So that is V into R2 divided by R1 plus R2. So this V is equals 30 volts and R2 is 20 ohm divided by 20 plus 15. That is 20 plus 15 is the total resistance. So hence I will get what is the voltage across resistance R2. Similarly, you can find out what is the voltage across R4, that is VB, that is supply voltage 30 volts into resistance R4 divided by R3 plus R4. So that is V into R4 divided by R3 plus R4, that is give me 30 into 5 divided by 10 plus 5, that is 10 volts. So VA is 17.14 and VB is 10 volts. So what is VAB then? So VAB is equal to VA minus VB. So VA is 17.14 and VB is 10 volt. So hence I will get VAB as 7.14 volts. Now we have got VTH, that is Thevenin voltage. Now we need to find out what is the Thevenin resistance. To find Thevenin resistance, what we have to do? We have to short the voltage source and then we have to find what is the resistance value looking back into these terminals. So when you look into this terminal, it's like R1 and R2 are parallel. That is connected in series with R3 and R4 parallel. So that is RTH is equals RAB is equals, that is R1 into R2 parallel, that is R1 into R2 divided by R1 plus R2 plus, that is in series with R3 and R4 parallel, so that is R3 into R4 divided by R3 plus R4. So substituting all the values, we get 8.57 plus 3.33, that is equal to 11.90 ohms. Now this is the RTH. Now redraw the Thevenin's equivalent circuit. That is VTH is 7.14 volts, RTH is 11.90 ohm. Sorry, VTH is 7.14 volts, RTH is 11.90 ohms, and connect back the load resistance. Now the question was to sorry. The question was to find the load resistance to which the maximum power is delivered and also the value of maximum power. So we need to find out what is RL. So to deliver maximum power to this load, what is the condition? RT TH or R circuit should be equal to R load. That is, RTH should be equal to RL. Then only the maximum power is delivered. So that means to say RL is equal to 11.90. And the value of maximum power is given by P max is equals VTH square divided by 4RL. That is maximum power equal VTH square divided by 4 RTH, that is 7.14 square divided by 4 into 11.90, that results into 1.07 watts, and the RL is equal to 11.90 ohms. So this is how we can solve the network using maximum power transfer theorem. So thank you.